All right, folks, so here we are. This is section 12.2, where we're going to be applying the EM algorithm to PCA. So if you haven't heard about EM, check out the previous video. We haven't covered it in the course of the book yet because we jumped to chapter 12. I think it's actually covered in chapter 9, but I gave it kind of a one video tutorial about it in the previous video. So go and have a look at that if you don't know, if you haven't heard of EM. Now, basically, we're going to be applying it to estimating the parameters of the PCA model, and those parameters are going to be essentially a basis for the principal subspace, the mean value that we're going to use for the training data, and also the additional noise parameter there. And we've already got in the previous section, we've already derived alternative methods for doing so. So we're going to just discuss a little bit about why one might want to apply EM to that, and then we'll talk about, we'll just go through the steps of EM as applied. That's kind of what we'll be doing here. We'll get a couple of formulas. I'll explain to you, what the formulas, where they come from. It's all just essentially turning the crank. But we might be able to get some insight into what they mean, and we'll get these update equations for the the basis for the principal subspace, the noise, etc. Then there'll be a little bit of a discussion here about, again, why you might want to do EM, its computational benefits, and then applying it in the case of just pure PCA. So when we kind of take the noise limit to 0, it has a particularly simple form and particularly quite intuitive. And finally, we'll just talk about a nice little example that he's got, which might be fun to simulate in the future, actually, of what this looks like in 2D in the case of kind of rods on in case of actually balls on a rod, basically. If we look at it's kind of a cool picture of what EM looks like in kind of a physical setting. So that might be something fun to dig into in a future video. Cool. Okay, so let's have a look. What are we? What is this section all about? Okay, so he says, the probabilistic PCA can be expressed as in terms of marginalization over a continuous latent space Z, in which for each data point there's a corresponding latent variable, right? So if we want to figure out that those the principal subspace, the noise value, and then the noise parameter, well, it's useful to assume that there is for each data point there's going to be this lower dimensional latent variable that's generating that data point, offsetting it with some mean and adding some noise. And this is this is setting up kind of maximum likelihood estimation with latent variables is exactly where you want to apply EM. So we can therefore make use of the EM algorithm to find maximum likelihood estimates of the model parameters. Now, this may seem rather pointless because we've already obtained an exact closed form solution for the maximum likelihood parameter values before, so we've already done this. But it's going to be useful because in spaces of high dimensionality, there may be computational advantages in using an iterative EM procedure rather than working directly with the sample covariance matrix. So we'll talk about this towards the end, but it's like, if the dimensionality of your data, the number of elements it has when it arrives, its extrinsic dimensionality is like to 1,000 or larger, and this is very common these days. And you have a 10,000 by 10,000 matrix to invert, and a covariance matrix to invert, and things scale by 10,000 to the cubed. I mean, my goodness. So it's going to be a lot of work. So you might be able to avoid that. This EM procedure can also be extended to factor analysis, which we haven't talked about yet, and it also allows us to handle missing data in a principled way. So lots of advantages for this. So the EM algorithm for probabilistic PCA, we're going to derive it. We just have the kind of usual EM machinery. So remember what we had to do was we have to get so in the E step we would look at the latent variables and we would determine the posterior distribution on the latent variables given the previous set of parameters. And in the M step, we would take the expectation of the log likelihood of the joint distribution of the data and the latent variables, and then we would maximize with respect to the parameters there. So it's kind of a simple procedure, and we justified why we did that as kind of coordinate descent on the elbow, the negative variational free energy in the previous video. Okay, so So thus we write down the complete data log likelihood and take its expectation with respect to the posterior distribution, the latent distribution, so which we got from the E step, evaluated using the old parameter values. Maximization of this expected complete data log likelihood then yields the new parameter values, and we just do this back and forth. So it's kind of a very mechanical procedure. So now, how does it work for our PCA data? Let me just erase some of this. Okay, we'll write it as we go. Okay, so what does it look like? Now, because the data points, you can see that, are assumed independent, the complete data log likelihood takes the form. So notice that we've got our data, we've got our latent values, and then we've got the parameters we're interested in. So this is a complete data likelihood, right? The parameters sitting on the right side are either getting conditioned on. And because we're assuming they're independent, well, we get contributions from each of the terms. Okay, and we're just applying, just splitting up each data point as a contribution from the prior times the likelihood of that latent variable. Okay, now we already, so in principle, so mu is going to be one of the parameters, but to make our life a little bit easier, we already know that the exact maximum likelihood for a solution is the sample mean, so let's just plug that in right away. And then making use of various expressions, taking the expectation with respect to the posterior distribution gives us this giant thing. Okay, so this is it might look a little bit, maybe it looks a bit scary, but it's all it is this is essentially just a couple of Gaussian terms, right? And with a minor tweak that we do. So remember what our model was? We had that, this P of xn here was, you guys can see me, okay. So this was xn, so this was going to be w times zn plus the mean, and then there's going to be some noise, right? That's what that was. And then this thing was going to be, it was just going to be of zn was 0 and I, so it's going to be 1 for each one of the along each element. Okay, so all you do is you just write that out, and you take the logarithm, so all the exponentials disappear, and then you just get a bunch of terms showing up. So for example, like this thing, well, what's that going to look like, right? When we take the logarithm of it, so it's going to end up with, like, there's going to be a minus 1 over 2 Zn transpose Zn. That's going to show up, and we're going to have one of those. So that's going to come from the exponential for from the Gaussian. Okay, so the only thing we're going to do that's going to be maybe a little bit unexpected for you is we're just going to write this as this is equal to the trace of Zn transpose. Okay, so that's where, like, all of these little terms come in. There's a similar thing going on here. So this is actually being contributed from this particular term, right? When you multiply that out, you're going to get a term that's wzn transpose wzn. Well, that's this, but normally the zn would be sitting on this side, right? So the way it would show up would be as zn transpose wt wzn. Well, we just write this as to kind of allow us to kind of group the terms as zn transpose times wt w using the cyclic property of the trace. Okay, so that's all it is. There's nothing magical happening here. It's just literally expanding that for our Gaussian model and applying this little trace property. Okay, so that's getting us this part, and then we just take expectations. And so the expectations are over the latent variable. So we have to, these z's are multiplying, so we take their expectation. Here's a z by itself, and then here's again their product. So we've already, and these are with respect, so this expectation is with respect to, probability of z given x, and we're just gonna say like the old values basically from the previous time step. Okay, so that's all it is. All right, so now we need to be able to evaluate these parameters. So imagine we've got all values of w. How do we actually fill in these expectations that we need? And it's pretty simple. So we already found out in, I think it was the last section or something like that, that in this model, the probability, so the posterior probability on the latents is also Gaussian. So given all the parameters, it's going to have some mean, which is this, and then it's going to have some covariance, which is this. Okay, so so we just write down the mean. Well, that's what it is. And well, we don't actually need the covariance directly. What we need is this expectation of the outer product, but that comes from, we can just write that in terms of the covariance, right? So this is just using this very important formula, which you should know by now, and if you don't, definitely learn it. We just plug in, we know what the covariance is, it's that thing, and we've got the other bits that we need. Okay, so that's all this. So we've got those values, and now we're going to maximize. Okay, so we maximize with respect to W and sigma squared, keeping the posterior statistics fixed. So we've now kind of plugged in these expectations. What are we going to get? So these guys we're going to have plugged in with the old values, and now all we do is we're just going to take the mean with respect to the derivatives with respect to W and with respect to sigma squared, and set them to 0. Okay, so if we do that, again, it's a good chance to practice your, let me erase some of this stuff. It's a good chance to practice your, matrix, differentiation, but you'll get some simple terms. So, for example, let's just do the W one. So this thing is going to give us, it's going to, if we take the differential of it, we're just going to get terms showing up that look like E, Zn transpose. And so that's going to be contributing that component. And then here, what are we going to get? Well, if we put a dW in there, well, it's going to be, it's going to give us an WE kind of ZZ. And I think it should do the exact, so there'll be 2 of that. It will cancel this. Things will work out really nicely. We set these things to 0, and you end up with something. I'll let you fill in the details, but it's basically going to look exactly like this. Okay, so you're going to have this outer product, the sum of outer products of the mean subtracted data points, outer products with their with the expected value of their latents, and then some inversion happening. Okay, so now the question is, this is what will come out. What does it actually mean? Well, effectively, I think, sometimes these formulas can be a bit mysterious. They often still are, to me, but these ones we can actually kind of work with. So essentially what's happening here is you can imagine the situation. Let's see how far you guys can see. So I'm just going to put the line here so I can essentially see the limit of where you can. Okay, so essentially what we're doing is, let's just call this, we'll call this like the mean subtracted data. So, and we'll see this again actually when we talk about PCA itself. So suppose that we were trying to say this was actually equal to W times Z, right? Because that is kind of what we're saying, that the observations, mean subtracted observations, are just the projections of the latent variables according to W with some noise. Okay, so now we want to minimize, because of our Gaussian assumption on the noise, we end up wanting to minimize this. And it turns out that actually, so if you actually just run this minimization through, the W that you get looks exactly like, it's going to be X times Z transpose times Z transpose minus 1. So this is essentially what's happening here. It's just that, so W is just, this is kind of the formula for, finding, finding this kind of projection matrix, the principal, the basis, the principal subspace, etc. It's just that we don't have the Z, so we just plug in the expected value of the things that we need. And that's kind of, I guess, one of the cool aspects of EM, that allows you to kind of work with your with missing data by kind of guessing its values and using it that way. Okay, so that's kind of what this whole thing is about. And this this formula down here, again, this is just really simple. All you're doing is you're just subtracting out for each data point. You are just subtracting out, it's going to be xn. You're subtracting out W times Zn minus. You're just kind of summing all of those up, because and that's going to give you essentially the variance term, right? Because that's, in our model, that is what the variance is. The whatever is left of in this residual is that noise is going to have this variance on an element-wise basis, and that's all you're computing here, right? So all of these terms, again, we're just doing that trace trick here. They're just coming from computing this. So that's where this comes from. You can figure it out by doing the derivative, but if you want to understand where it comes from, that's where it is. Okay, cool. All right, so the EM algorithm for probabilistic PCA proceeds by initializing parameters and then alternately computing the sufficient statistics of the latent space posterior distribution using these guys in the E step, and then revising the parameter values using 12.56, 12.57 in the M step. So that, and you just go back and forth. So that's basically, that's the algorithm covered. And why do you want to do this? So that's what we're going to talk about next. So unlike conventional PCA, based on an eigenvector decomposition of the sample covariance matrix, the EM approach is iterative. So let's highlight that. And so might appear to be less attractive. Like so previously we could just, instantaneously do the eigenvector decomposition and get the answer. However, each cycle of the EM algorithm can be computationally much more efficient than conventional PCA in spaces of high dimensionality, which is basically where we all live now. To see this, we note that the eigendecomposition of the covariance matrix requires OD cubed computation. So that's going to, I assume, I don't know where this comes from, but this is often the scaling you get when you're inverting matrices. So maybe it's related to that. Often we are interested only in the first m eigenvectors and their corresponding eigenvalues, in which case we can use algorithms that are OMD squared, okay? But you still got this D, this giant D hanging out. However, the evaluation of the covariance matrix itself takes this many computations, where n is the number of data points. So we have lots of data points, and very large dimensions. So this is still not great. Algorithms such as the snapshot method, which assume that the eigenvectors are linear combinations of the data vectors, avoid direct evaluation, but are ON cubed. So again, okay, you've traded n for D, but n is still going to be very large. Okay, so what do you do when you have, we're in the big data, right? High dimensional data and lots of it. Like, what do you do? The EM algorithm described here also does not construct the covariance matrix explicitly. The most computationally demanding steps are those involving sums over data set that are ONDM, right? So everything is like in single powers. So this can be, for large D, this can be a significant saving compared to OND squared and can offset the iterative nature. So let's do that, and okay. So and I think he's talking about, what are the steps? Like, so let's have a look at this. Try to kind of eyeball it a bit. So this is going to be what? This is going to be kind of D, D times M. And maybe this is where the n's coming from. So maybe this is one NDM thing going on here. So this is going to be an m squared situation, and you're going to be summing it up. But the overall result is going to be an m squared matrix. An m by m matrix. That's what's going to come out of that. And then you're going to invert this. So this will give you like a O m cubed for the inversion. But maybe actually the toughest part of that will be this n times m squared thing. And if m is small, and typically it will be much smaller, then maybe this this bit is going to kind of dominate. And I think this is all actually going to be quite easy to do. So I think that's what he's talking about. And so in kind of in the big data regime where D is large and n is large, EM can give you lots of savings, and the iterative aspect might end up being worth it. Assuming you don't have to iterate too much, I assume. Okay. Note that this EM algorithm can be implemented in an online form. Online is great, so every time, you can just update it with every new data point, in which each d-dimensional data point is read in and processed and then discarded before the next data point. To see this, note that the quantities evaluated in the E step, an m-dimensional vector and an m by m matrix. So that's going to be, I think he's talking about these guys. Can be computed for each data point separately, right? Because we computed, they're computed on a data point basis. And in the M step, we need to accumulate sums over data points, which we can do incrementally. This approach can be advantageous if both n and d are large. Yeah, so we're kind of doing all of these sums, and I guess M and D are, yeah. I mean, I guess, yeah, so obviously we can kind of split this stuff up into, and do it kind of one element at a time. I'm just trying to think, like, well, how, yes, so we can certainly compute this like one element at a time. How would it exactly work with, so what would you do? Compute one element at a time and then get the new updates, and then repeat the cycle again? I'm not exactly sure. So we'll leave that. We'll just take his word for it on that one. But at least from those formulas, we can see that, okay, just on those formulas taken alone, they clearly can be kind of split up on a per data point basis and seem amenable to kind of some kind of online computation. Okay. Yep, compute, and then the M step, okay, so this approach can be advantageous if both N and D are large. Okay, we now have a fully probabilistic model for PCA. We can deal with missing data, provided it's missing at random. So missing at random, if I recall this, so this is where the value, which data is missing doesn't depend on the values of the parameters. There's a good discussion of this on the probabilistic graphical models book, or at least that's where I've kind of come across it before, but I don't remember much more beyond that than that. It's just, I think it's actually an interesting concept, so worth reading about, because in case you come across missing data and have to deal with it. By marginalizing over the distribution of the unobserved variables, again, these missing values can be treated using the EM algorithm. You just assume they're hidden variables. And we give an example of the use of this approach for data visualization in figure 12.11. Okay. The second last thing, what happens when we take when we look at the ordinary PCA limit? So we assume the observation noise is 0. So another elegant feature of the EM approach is that we can take the limit of sigma squared going to 0, corresponding to standard PCA, and still obtain a valid EM-like algorithm. So that's pretty cool. Right. And we see that the only quantity we need to compute in the E step is E of Zn, right? So let's have a look at this. Right, because this is going to go to 0. So that's all we need, right? E of Zn is just the product of EZn, Znt is just a product of those guys. So we don't need to, so we won't need to compute anything fresh, which is good. Furthermore, in the M step is simplified because M is right, because we don't have this like additional term that was floating there anymore. To emphasize the simplicity of the algorithm, let us define X tilde to be the matrix of size n by d, whose nth row is given by blah blah blah. The E step of the EM algorithm for PCA then becomes this. Right, and look at what we're doing. So what does this look like? This is, we are projecting the observations into the space of into the old basis, basically, right? This is kind of the least squares projection, finding the least squares projection of the observations into the space, the coefficients of that. We see that the E step involves an orthogonal projection of the data points onto the current estimate for the principal subspace, right? So I think one way to remember that is, imagine this was just orthonormal. So this was the identity. Well, you're just projecting onto each one of those dimensions, basically. But you have to have this kind of correction term to account for the fact that your basis elements might not be, they'll have lengths and they won't be perpendicular. And this is kind of what we already saw before, right? So now once you have those latents, then what you're doing is now you're finding you're updating it, and you're finding the new projection weights that map the latents into the observations. So from our earlier discussion, we said the E step involves an orthogonal projection of data points onto the current estimate for the principal subspace. Correspondingly, the M step represents a re-estimation. So let's highlight that. In which the projections are fixed. Okay, so E step involves an orthogonal projection of data points in the current estimate, and then you're just going back and forth. So kind of like a natural thing that you might have come up with yourself. You didn't even know about EM, but now you know about EM, and so now you can have a sense of why it might work. And then finally, the very last is a simple analogy, which is easy to visualize for D equals 2 and M is 1. So we're looking for a one-dimensional subspace for two-dimensional data. So we have a collection of data points in 2 dimensions. Let the one-dimensional principal of subspace be represented by a solid rod. Okay, so here we go. Here is, can you guys quite see? Yeah, so here are our data points, and we have the rod. And so in the in the E step, we project the data points kind of in the least squares way onto that rod, and then the M step we kind of adjust the position of the rod to kind of minimize the energy. I guess he'll just say what that is. So let's have a look. So in the E step, we keep the rod fixed and allow the attachment points to slide up and down the rod so as to minimize the energy. And this causes each attachment to independently to position itself at the orthogonal projection of the corresponding data point onto the rod. In the M step, we keep the attachment points fixed and then release the rod and allow it to move to the minimum energy position. So we're just kind of like moving down this energy surface. The M steps are then repeated until a suitable convergence criterion is satisfied, as illustrated in figure. So there it is. So eventually it kind of settles on this. So that's pretty cool. I think it might be worth animating at some point actually, just to see it all happen, and also emphasize kind of the energy minimization that we're effectively doing. Like in real life, these two processes would happen at the same time, whereas here we're kind of alternating, back and forth between them. And it's an interesting question: under what settings, in which cases, they give the same answer, and I believe they don't always when it comes to like machine learning settings. Whereas I think in this physical setting they would. Okay, and then he's got, let's just zoom out a bit and look at this. So probabilistic PCA visualization of a portion of the oil flow data set for the first 100 data points. The left-hand plot shows the posterior mean projection of the data points on the principal subspace. The right-hand plot is obtained by first randomly omitting 30% of the variable values and using EM to handle the missing values. So kind of using EM to find their, most likely settings. At each stage, you would presumably set them to their get a distribution on them, and then infer the parameter, infer the principal subspace that way. Note that each data point then has at least one missing measurement, but that the plot is very similar to the one obtained without missing values. So just showing that, look, we can actually handle missing values in a principled way. That might be a fun example to also work through. But anyway, so I think that's basically what we've got. So we applied the EM procedure to PCA, and we got this really. So all we had to do in the E step, let's just erase all of this. So in the E step, we just had to estimate these values, and that came from forming the log. So the log of the joint distribution of the observations, the hidden variables, taking the expectation with respect to the taking the expectation of the latent variables with respect to using the old parameter values, getting this, and then maximizing. So that's we plugged in, and then we maximized. We held those fixed. We maximized with respect to the parameters, and we got these expressions, which ended up having kind of very, despite their appearance, having kind of very natural interpretations, as recalculating the principal subspace and finding the residual variance. Cool. Okay, so I think that's all I wanted to talk about for this section, and next time we will continue with Bayesian PCA. So hopefully you will join me then. Bye.